Welcome back to the 15th video about the mighty Melexis MLX90363 Triaxis magnetometer. In the previous video, we went 3D and measured the alpha and the beta angle of the magnetic field going through the chip, like you would use in a joystick application. Card here, link in the description. However, our measurements, while working in principle, were not really precise and quite distorted. The reason being, we didn't calibrate that thing for 3D measurements. And that's exactly what we will do in this video. Enjoy! The calibration of the 3D formulas is done via the parameters KALPHA, KBETA and KT. They are all 16-bit parameters, which obviously, if you look at the default values, are translated into some floats. And the default values given here in the datasheet are for KALPHA 0, for KBETA 1.6, and for KT just 1. Chapter 16.4 gives us some more information about these three parameters. As we already know, they are all 16-bit parameters that are translated to floats, to be more specific, into a float range between 0 and 2. We also get here some typical values for KALPHA and KBETA 1.2 and for KT 1. While KT is usually 1, we will see later on. However, our default values are quite different from the typical values. So, for example, we get here for KALPHA a default value of 0.0. which explains why our alpha angle we measured was really distorted and capped off and didn't make really sense. We already had a detailed look at the formulas for the alpha and the beta angle in 3D mode as they are given in chapter 16.2 in the previous video. However, back then we completely ignored these KALPHA, KBETA and KT parameters. So, within the formula for the alpha angle, KALPHA scales our B3 signal, that's by default the Z signal, in relation to the B2, so by default the Y signal. And within the formula for the beta angle, KBETA does the same, but in relation to the B1 signal, that is by default the X signal. And we really need to scale the B3, that is Z signals, to the same levels as the B1 and B2, that is X and Y signals. Otherwise, the numerators in our angle formulas wouldn't describe a circle, but some points for probably on an ellipse. And then our further angle calculations for alpha and beta go all haywire, as we have seen in the previous video. KT leaves me scratching my head because I don't really understand it, and that's really all the information in the datasheet we have about it. So just looking at the top formula for the alpha angle, you could use KT to scale the B2, that is Y signal, in relation to the B1 signal, which could also be necessary. But then we use the same KT in the beta formula to scale the X, that is B1 signal, to the Y, that is B2 signal. That is, in effect, you cannot use KT to scale B1 to B2 and vice versa. Unless, of course, these formulas are not quite correct. But we will find that out in the future, hopefully. Before we proceed, I wanted to point out that our magnet here sits at a 45-degree angle over our chip as it rotates. So all three axes see that magnet or the magnetic field lines at a either plus or minus 45-degree angle at some point. Meaning we can really scale according to what we see later on the serial plotter. Let's dive right into the sketch to experiment with KALPHA and KBETA. So in the setup, I noted down here the update statements for KALPHA and KBETA and KT to their respective default values, just in case I want to reset them to the defaults in the future. Then we still have a fixed gain of 3, and of course 3D is set to true, and later on I will first set KALPHA and KBETA to 1.0. So basically no scaling of the z-axis for either the alpha or the beta formula. My headings for the serial plotter now also contain KALPHA times B3 and KBETA times B3 because, yeah, we will now use that scaling. And in the loop, I also print out a KALPHA times B3 and KBETA times B3. Now, this is almost the same picture as we saw last time. You remember I said alpha is quite distorted because, yeah, KALPHA is set to 0, which makes absolutely no sense. And equivalently, the KALPHA B3 line is nowhere to be seen because it's overlapping with our 0 line. But we see here in lilac the scale by default of the factor 1.6 scaled up KBETA B3 line. In green is the original signal. So, yeah, now that we've seen what we already saw in the last video, let me quickly uncomment these two lines and set KALPHA and KBETA to 1, and then we have a look-see again. And that looks already much better. So our B3 line, our KALPHA times B3 and KBETA times B3 lines are, of course, all identical now. But what you can see is that the, the alpha angle, yeah, is now really, a proper angle reading somewhere between, yeah, let's say 75 degrees and 140 degrees. It should be between 45 and 135 degrees. You remember we have a 90-degree angle, so we're starting at 45 degrees, we add 90 degrees, we end up at, on the other side of the rotation, at 135 degrees. So still room for improvement. Maybe I should put these lines in there, you know, 45 and 135. But for now, what we can see is that our Z data, B3 data, is from the amplitude far too high. So we need to get that down here into that range. And if I look here at the maximums, we are about at, let's say, 1200, and we are here at 4000. So let me experiment a little bit with the KALPHA and KBETA factors, and then I'll come back to you. So I fine-tuned KALPHA and KBETA each to 0.3 now, and I'm printing out, instead of a 0 and 180 degree line, our targets of 45 degrees and 135 degrees. And of course, I adjusted that here in the serial print also, printing out the values 450 degrees and 1350 degrees. Remember, I scale up my degrees by a factor of 10. And look at that. So here is our raw B3 respectively set signal, and that is now here scaled down again in lilac at the same level, maximum level, aboutish as our blue B1X signal and reddish B2Y signal. And suddenly our angle measurements here make a lot more sense. So we have still black the alpha angle and blue the beta angle, and they are nicely 90 degrees phase shifted. Amplitude wise they are still a wee bit distorted, so you could probably fine-tune those parameters even more, but I guess a lot of that distortion stems from how my little test jig here is built. It's you know. Anyway, there is one thing I really want to try out still. I want to test if KT is really used in the formulas as shown in the datasheet. Therefore, I set KT here to 1.5. That will just distort our measurements, of course. But if the angle readings from the chip and the ones we calculate in our own code are still the same, then we at least know that the formulas given in the datasheet are correct. And indeed, the alpha and beta angle returned from the chip still overlap with the alpha and beta angle we calculate. As we can see, there are no two curves, they are overlapping. Perfect. So at least there, even if it doesn't make sense from my perspective, the datasheet is correct for once. If you have any idea what you can actually do with that KT parameter, let me know in the comments. That was 3D and it works as described in the datasheet, which is good. However, there is one parameter not specific to 3D, at least not according to the datasheet, which I want to revisit. We already tested that hysteresis filter, FHYST parameter, in video 12. Card here, link in the description. Just a short recap, it's an 8-bit value in the range between 0 and 255, and it translates with one LSB equal to 0.044 degrees to a float value between 0 degrees and 11.22 degrees. And according to the description here, it's not updating the output when the change in angle is below the hysteresis we are setting here. So we are expecting a stepped output somehow if we set F hysteresis to a value not equal to 0. And as mentioned before, in 2D mode in video 12, that didn't work so well. We just got a delayed output signal, but not, a hysteresis stepped output signal. So let's test that again in 3D mode. For that purpose, I first reset KT back to its default value of 1.0. And then I set F hysteresis raw, so the integer value, to 255. And let's see if we see any effect on the serial plotter. And again, the FHYST parameter does something. So we have here in light blue and dark blue, light blue our own calculated beta angle, and dark blue the beta angle returned from the chip. And we don't see a delay like in 2D mode, but we now see here something, yeah, I don't know how to describe it. I mean, sometimes it overshoots, then it undershoots, and yeah, it looks like digital noise suddenly introduced. So I have no idea. And if we look at the alpha angles, so gray and black here, black, the signal returned from the chip, it's delayed and capped off at the top and the bottom. It makes absolutely no sense. Absolutely no sense. So I think, I mean, obviously, we are hitting the parameter in the EEPROM, or something in the EEPROM, but yeah, no, doesn't work. Simply doesn't work. Yeah. That's it for today, and for now also for the Melexis MLX90363. I think we covered everything that can be covered without, you know, working directly with a Melexis engineer, which is a wee bit beyond me, but maybe I'll try. Anyway, we have basically two things we didn't understood about the chip and we couldn't get to work. And this was first the auth parameters, specifically the auth B1, B2 parameter, and second, that FHYST parameter. Everything else seems to work and the library does what's expected of it. So, yeah, next steps, probably application of that chip in an actual 3D joystick. And I don't talk about just X and Y, I also talk about rotation. So we probably will need two of those in that joystick, however it will look like in the end. But that's a larger project and I'll have to think a little bit about it. So we probably do something in between. Anyway, till next time, bye.